So here we're going to look at how we actually can undo a Laplace transform, and then how we can actually use them to solve a differential equation, which means we need to know how to transform a derivative because differential equations involve derivatives. So we're going to start off looking at how we do inverse Laplace transforms. As a reminder, a Laplace transform of f of t is capital F of s. We're changing to a new function and we're changing to a new independent variable. F of t is the inverse of f of s. So f of t is the inverse Laplace of capital F of s. Okay. So as a reminder, we have tables of Laplace transforms. They are in the book. They're also online. You can search them online. They do change a little bit depending on the one you find. So you want to look at yours and try to find out what you have. We're going to go ahead and find some Laplace transforms and see what happens here, and find out what those answers are. So let's do the Laplace transform of 1 over s to the 4th. So again, I'm going to go look at this. I'm going to look at my table. I'm going to look for 1 over s to the 4th. I have a 1 over s, close, but not exactly. I have a 1 over s squared, again, close, but not exactly. Then I notice I have an n factorial over s plus, to the n plus 1. So that looks like it would probably work for us. So we have n factorial over s to the n plus 1. So comparing that, we have 4 here, which tells me my n must be 3, because 3 plus 1 is 4. That means I need a 3 factorial in the top. 3 factorial would be 3 times 2 times 1, or 6. So I actually need a 6 in my numerator. So let's think about this for a moment. In order to get a 6 up here, I can put a 6 up there, but that means I need to divide by 6, because otherwise I've changed the problem. So let's divide by 6. So we didn't change the problem. Just as with Laplace transforms, I can actually factor that 6 out. We did that with Laplace transforms. Inverse Laplaces have the same property, so I can pull that 6 out. So I now have a 1/6 in the front, Laplace transform of 6 over s to the 4th. And so remember, 6 is 3 factorial. So now looking at this formula here, I now do in fact have 3 factorial over s to the 3 plus 1, or 4. And that is going to be t to the n. So that transforms back at the 1/6 there. My n was 3, so that'll be 2 to the t to the 3. And that's all there is to finding an inverse Laplace. Let's do another one. Let's try this one, the inverse Laplace of 10s over s squared plus 16. I do want to make the comment that the inverse Laplace of a linear combination of alpha times f of s plus beta times g of s is going to be alpha times the inverse Laplace of f of s plus beta times the inverse Laplace of g of s. So that still works just as we did before. So now we can go ahead and find this one. I'm going to go ahead and think about what this is. Again, that 10 may not be of use to me. So I'm going to pull that 10 out. So just to reiterate what we have 10 times s over s squared plus 16. Pull the 10 out because I know I now can do that because I have that property that I just gave you. So I have 10 times the inverse Laplace of s over s squared plus 16. So now I go look at my table again. I'm looking through this table and I'm looking for s over s squared plus 16 or something like that. And I happen to notice right here that I have an s over s squared plus k squared. All I gotta do is figure out what my k is, and then I see that that's the cosine of kt. So let's see if we can figure out what the k is. Oops, wrong one. Remember that? So let's see if we can figure out what that k is. If this is s squared over k squared, that means k squared must be 16, which means k is 4. You don't need the plus or minus. We are going to use all positives here, mostly because the cosine of the positive would be, the negative would be the same. But it also, we don't need to worry about that in these cases when we're doing Laplace transforms. But now I know my k is 4. So I know that this will transform as 10 times the cosine of kt. So k we just found out was 4. So we can actually put in 4t. So this is 10 times the cosine of 4t. Let's try a couple more. Let's find the inverse Laplace of s plus 1 over s squared plus 2. Now, if I go and look at my table, I'm going to look through my table and I don't see an s plus something over s squared plus something. I don't see that anywhere here. I've got lots of things like it, but I don't really see that exact one. I see an s squared plus k squared, but I don't really see what I'm looking for. So I don't see exactly that. So what I need to do is sometimes I need to actually do changes into two separate fractions, which means I need to do partial fraction decomposition. Your technology will actually do this for you, or you can go ahead and do it by hand. Remember, with partial fraction decomposition, s squared plus 1 over s squared plus 2 would be where you would have to look for a over s squared plus 2 plus b over s, where you have to factor that. Actually, I'm sorry, you don't need to do that with this one. I apologize. This one's not partial fraction decomposition. This is one a little bit easier. We will have to use that, but this one's a bit easier. If I notice here, I don't like having this top with two things. I can actually separate these up. It is the inverse Laplace of s over s squared plus 2 plus the inverse Laplace of 1 over s squared plus 2. So I apologize. I was thinking this was a little bit more involved, but it's not that involved. You just did separate in two separate fractions. Now I can go look at my formulas here. I'm looking for s over s squared plus something. And I notice I do in fact see that here. I see an s over s squared plus k squared. That is the cosine of kt. All we gotta do is figure out what that k is. So again, in this, we're gonna have s squared plus k squared. K squared therefore must be 2, so k is the square root of 2. I also have a 1 over s squared plus 2. Again, looking at my table, I do see where I have a number over k squared plus s squared plus k squared. That is the sine of kt. So again, I got to first figure out what my k is. So s squared plus k squared is my bottom. So that must mean k squared is again 2. So k is the square root of 2. So great, that's what k is. We're good here. But then one of the things I notice is that it should have a k in the top. So I need to put in a square root of 2 in the top. But if I put a square root of 2 in the top, I've just changed my problem. So I need to also put a k square root of 2 in the bottom. So I don't change my problem. So now where I am, I can actually now do these nice little integral Laplace transforms, inverse Laplace. This first one is just the cosine of kt. K is square root of 2t. The second one is I'm gonna have to bring that 1 over the square root of 2 out. And then the rest of it's going to be the sine of kt. And the k again was square root of 2. So there is that inverse Laplace. We'll do another one. This one is 1 over s squared plus s minus 20. Again, if you go looking through here, some of these you might actually see something like that. Some of them you don't. So I'm going to show you what we do, how to do this without doing that. First thing I notice is that I usually need to have a factor in the bottom. So let's factor the bottom. So that factors into s minus 4 and s plus 5. Again, you might actually see one that does that has that same kind of idea, but I want to show you what happens if it's not there. I guess I do have one there, but I'm going to show you what happens if it's not actually there. And what do we do in this case? And what we would do in this case is we actually, again, I mentioned this already once, you have to do partial fraction decomposition to separate into separate fractions. So as a reminder, that would mean you'd have 1 over s minus 4 times s plus 5. That factors that separates into s 4 over s minus 4. Sorry, not 4, a over s minus 4 and b over s plus 5. Then you would multiply through by the common denominator and then equate and find out what a and b are. Or you can use your technology. Technology will do this for you. It turns out that a is 1/9 and b is also 1/9. So that means that this becomes the inverse Laplace of 1 over s squared plus s minus 20 becomes the inverse Laplace of 1/9 1 over s plus s minus 4 plus 1/9 over 1 over s plus 5. Again, you can use technology for this. Oh, I actually have a slight mistake. This is actually minus 1/9. So this is minus 1/9 there. All right. Now, when you go looking through this, you can go and see that you have an s minus 4. So you're looking for an s minus something. I now notice when I have an s minus something in the bottom, that that is e to the at. In this case, it's s minus a. So I now know that this would actually do an inverse Laplace of 1/9 e to the minus, it's a 4 there, so it's a 4t because it's e to the at. It is s minus that a, so that a is 4, minus 1/9 e to the 5t. But be careful, it's not positive. Remember, it is s minus a, which means in this case, a, it must be negative 5. So this one's actually e to the minus 5t. All right. We do also want to talk about transforming a derivative. There's a theorem that we're going to look at here. That theorem says that f of t be a function such that both f and f prime have Laplace transforms. Not every function has a Laplace transform because that integral may not exist. It might not converge. So we need to first make sure they do in fact have Laplace transforms. Then if they do, then the Laplace transform of f prime of t is s times Laplace transform of f of t minus f of 0, which means you need to know your initial condition. This is why I said Laplace transforms are useful when we know that initial condition. I'm going to go ahead and prove this to you. Show you that this in fact is true. So the first thing to do is we want to, usually when we're proving things, we start with one side. The more complicated side in this case is actually the Laplace transform of the derivative. So we're going to start with that side. The Laplace transform is the integral from 0 to infinity of e to the minus st times f prime of t, pt. So remember, it's e to the minus st times whatever function we're trying to do the Laplace of. In this case, it's f prime. All right, well, that doesn't look great. Let's see what we can do with that. Well, first thing I'm going to do is take this improper integral and write it as the limit as b goes to infinity of integral from 0 to b of e to the minus st f prime of t dt. And then we're going to use the fact that we're going to do u substitution. I'm sorry, integration by parts. We're going to let u equal e to the minus st. We're going to let dv equal everything left over, which is f prime of t dt. I'm then going to find out what du is. Du is going to equal negative s e to the negative st dt. And v is going to equal f of t. Okay, so we're just doing integration by parts here. No big deal here. We now can substitute those in. And we have the limit as b goes to infinity of u, which is e to the minus st, times v, which is f of t. We're going to evaluate that from 0 to b, minus the integral from 0 to b of u dv. I got to remember my formulas. So integration by parts is u times v minus the integral of v du. So that would be minus s e to the minus st times f of t dt. All right, cool. We have that now. So let's see where we can go from here. I'm going to go ahead and evaluate this one integral. It's one part. So I have the limit as b goes to infinity of e to the minus s times b, f of b, minus e to the 0 times f of 0, minus, or let's do plus s, because we're going to bring that s out, changes the sign, e integral from 0 to b, e to the minus s of st, f of t dt. Okay. Let's go ahead and do this limit. This limit of the first thing, e to the minus sb, will go to 0 as b goes to infinity. That will take over, so you'll get 0 there. E to the 0, of course, is 1. F of 0 doesn't involve a b, so it's just minus f of 0. This s times this integral, that is the Laplace transform of f of t. So we can put this back into that form, and we're now done. We have s times the Laplace transform of f of t minus f of 0. All right. Another theorem that we can also have, we can do higher order ones. We can, as long as f is a function such that f prime, the nth derivative of f, have Laplace transforms, then the Laplace transform of the nth derivative of f is s to the n times the Laplace transform of f minus s of n minus 1, f of 0, minus s to the n minus 2, f prime of 0, all the way down to minus f to the n minus first derivative of 0. So again, you do need to have an initial conditions. Remember, you have an nth order differential equation, you need to have n minus 1 initial conditions. We can then solve a differential equation using this idea. So let's go ahead and do one example of this. So we're going to go ahead and do this to solve this. We're going to do an example, but I just want to kind of show you the process. You're going to take the Laplace transform of both sides. Remember, you have the Laplace transform of a derivative using those formulas. And so let's go ahead and actually do this for an example. It's much easier to do with an example. So we've got y double prime minus 4y prime plus equals 6 e to the 3t minus 3 e to the negative t. Y of 0 is 1, and y prime of 0 is negative 1. So as I said, the first thing to do is take the Laplace transform of both sides of the equation. So the Laplace transform of y double prime minus 4 Laplace transform of y prime equals 6 times the Laplace transform of e to the 3t minus 3 times the Laplace transform of e to the minus t. Now that we've done that, Laplace transform of y double prime is going to be sorry, I have to always go look up my formulas. So this is going to be s squared times, we're using y, so instead of using f, I use y. So y of s, it is a capital Y, just kind of, it's like a capital F there. So this is the Laplace transform of y, is y of s. And then remember, it then goes minus s times y of 0 minus y prime of 0. So think of it this way, you're reducing your s from whatever, you start with s be the same power as your derivative. You start with y of s, you then reduce the s down by 1 power, so it's going to be s squared, then s, then no s. And then you increase your y of 0, then y prime of 0. So you're increasing, you're going from y to the to just y of 0, then y prime of 0. Now minus 4 times the Laplace transform of s of y prime is going to be s times y of s minus y of 0, minus s squared times y of 0, sorry. All right. Oh no, not s squared, minus just y of 0, because the s goes away, reduces down in power, as I just said, and you then start with the y of 0. Okay. Then we have to do the other side. This is where you will need to look it up in your table. E to the 3t is going to always transform as 1 over s minus whatever that a is. In this case, the a is 3. So we have 6 times 1 over s minus 3. Minus 3, again, e to a power is 1 over s minus whatever the a is. In this case, the a is 1 minus 1. So it's going to be s plus 1 in the bottom. Okay. So this looks like a mess. Now we have to figure out what to do with this. One thing to do with this is to maybe multiply everything out, collect like terms. Also, we'll put in what y of 0 and what y prime of 0 is equal to. So we're going to have s squared times y of s minus s times y 0, if you remember, was 1. Y prime of 0 was negative 1. Minus 4 times 4y of s minus y0 was again 1, and equals 6 over s minus 3 over s plus 1. Okay. Now I'm going to go ahead and still distribute through. So I've got s squared y of s minus s plus 1 minus 4 times s times y of s plus 4 equals 6 over s minus 3 over s plus 1. Okay. So now let's see what we can do with this. One of the things I notice is that I have 2 terms that have a y of s in them. So since I have 2 terms with a y of s in them, let's get those together. We want to solve for that. That's the part I should point out, is that the whole point is you want to find out what y is. So we want to find y of s by itself so we can do the Laplace transform, inverse Laplace. So we're going to get both terms that have a y of s in them together. Anything that doesn't have a y of s, take it to this side. So we know we have an s squared minus 4 times s times y of s is equal to 6 over s minus 3 minus 3 over s plus 1. I would then add s to both sides. I have a 1 plus 4 is 5. I'm going to subtract 5 from both sides. Okay. I therefore want to get y of s by itself, so I'm going to divide through by s squared minus 4s. So we have 6 over s minus 3 times s squared minus 4 times s minus 3 over s plus 1 times s squared minus 4s plus s over s squared minus 4s minus 5 over s squared minus 4s. Okay. So now let's see what we can do with this. One of the things I noticed, again, I have some, looks like some partial fraction decomposition I need to do here. So you don't want to have two terms like this multiplied together. You don't want to have two factors in the denominator. You want to do partial fraction decomposition. In most cases, there are cases where we don't do that, but in most cases you do. So I'm going to first find out what that is. Turns out that that's going to be minus 3 over 5 times s plus 1 minus 2 over s minus 3 plus 18 over 5 times s squared, I'm sorry, s minus 4. I think that was just one part of this that I was doing, and then I actually combined like terms. So I'm actually going to just tell you that's just one part of this that I did. I'm then going to go ahead and combine all my like terms together and find out what I end up with. So I'm going to actually erase this just because this is just part of what I'm going to have. But when you can do this all at once, by the way, you can actually put all this in your technology and ask your technology to find all of that partial fraction decomposition if you want to. And we're going to end up with minus 2 over s minus 3. Notice there is an s minus 3 here, and there's one down here. Plus 3 over 2 times s minus 4. You sort of have an s minus 4. You have an s squared minus 4s. The s will be pulled out. You're going to have a plus 1 over 2 times s. That's where that s came from there. Then we're going to have minus 3 over 5 times s plus 1. Again, that s plus 1 came from there. So when you decomposition this one, you'll get that. Minus 3 over 20 times s minus 4. Again, that came from there. Then we have a plus 3 over 4s, when again, the s came from the fact that we have s squared minus 4s. I factored the s out. Then we have plus 1 over s minus 4. Again, you gain that from here. You've got, I actually factored the s out. Actually, in this one, I just factored the s out. Notice the s is canceled. So you get 1 over s minus 4. And then minus, in this case, this one, actually, you would have to do some decomposition, factor the s out. You'll get plus 5 over 4 times s minus 4. And then minus 5 over 4 times s. So this is where technology is useful for this. This is why some people didn't like Laplace transforms before we had technology, but since technology would do this for us, it works out much nicer. And now all I have to do is take the inverse Laplace of all the terms. So you now would do inverse Laplace of all terms. So this is the process we go through. The process we go through is we first do the Laplace transform of both sides. Then we multiply everything out, collect all of our like terms, solve for y of s, and then do the inverse Laplace of all terms. So now what I end up with is the inverse Laplace of y of s is y of t. The inverse Laplace of -2 over s minus 3, well, that'll be -2 e to the 3t, because remember 1 over s minus a is e to the at. Plus 2/3 e to the plus 4t. Plus 1/2. 1 over s is just 1, so just plus 1/2. Minus 3/5 e to the minus t, because again, you had s plus 1, which will give you a minus 1, minus a. Then minus 3/20 e to the 4t again. Plus 3/4, just 3/4, because 1 over s, inverse Laplace is just 1. Plus e to the 4t. Plus 5/4 e to the 4t. Minus 5/4. At this point, I would probably collect any like terms I happen to have. When I do that, I get minus 2 e to the 3t plus 18/5 e to the 4t minus 3/5 I seem to have lost one of my terms. Oh, I did. I lost this 3/5 here. Oops. This 3/5 e to the t is right there. Oh, I didn't lose it. I just forgot that I have it. So minus 3/5 e to the negative t. Collecting all your other like terms, it turns out you're going to get the 1/2, 3/4, and negative 5/4 all go to 0 when you add them together. So there's your answer. And that's how we solve using the Laplace transforms to solve an initial value problem.